Good morning, everyone. My name is Priyanka Kattapogu. I'm from Amaravati. Recently, I have completed my post graduation from Vellore Institute of Technology. I'm doing this work under the guidance of Dr. Atul Shankar Manati sir. And my work is about low power, high speed modified GDA full ladder implemented by NCFET technologies. Coming to introduction, as we all of know about the full adder is the basic functional unit of an ALU and it has the ability to perform complex arithmetic operations. And this is the normal block diagram of the full adder. It is having a three inputs and the corresponding to output sum and carry. Sum and carry is carried out by for sum equal to A XOR B XOR C and for carry AB plus BC in plus C in A. Full adders plays a critical role in the implementation of arithmetic circuits such as multipliers, adders, subtractors, comparators, processors. And coming to existed methods, these are some of the existed full adders which are implemented with different techniques. Coming to this table here, this table is corresponding full adders with respect to their average powers and the delays. This is a 28 transistor full adder which will having the average power of 3.87 microvolts and it is having the delay of 48.47 picoseconds. Coming to 20 transistor, it is having the average power of 4.01 microvolts and the delay is 43.034 picosecond and so on. If we observe here, some of them having the low power and some of them having the lower delay. So overall, we try to reduce the transistor count and try to reduce the power consumption and speed of the circuit. So these are some of the proposed methods. First, we will discuss about the gate diffusion input technique. Gate diffusion input technique is nothing but it is more flexible as compared to CMOS design, and GDA technique is able to apply for low power digital circuit designs, which will allow minimum chip area, delay and low power consumption in order to reduce the usage of transistor. If we reduce the transistor count, the silicon chip area will also reduce, which will help to design the circuit in chip mode. And this is the basic diagram of the GDSL. It is having three inputs and one output. It looks like a normal CMOS inverter, but normal CMOS inverter having the single input and single output, but whereas coming to this GDSL, it is having three inputs and one output. And with the help of these three inputs, we are performing various logical functions on GDSL. And coming to this, it is a four transistor XOR logic which will be implemented by using the concept of GDI. Coming to this, this is the full adder implemented by using the 10 transistors with the help of GDA technique, and it is the corresponding output response of this 10 transistor full adder. If we observe at the output, there is a voltage degradation in the output because um, here there is two drawbacks in the 10 transistor full adder. One is degraded in the output and second one is the bulk end is not properly biased in GDSL, so that at the output stage of GD it is not feasible to get a strong 1 and strong 0 as outputs. So that we move to the modified GDA technique. In this modified GDA technique, the bulk node of PMOS transistor is connected to the VDD and the bulk node of NMOS transistor is connected to the ground, and a full adder is implemented by using 8 transistors with modified GDA technique concept, and this is the corresponding output response of this modified GDA technique full adder. So if we observe in this output, it improves the swing degradation, nothing but previously in GD technique there is a swing degradation in the output, but whereas in by using the modified GD technique we implement full adder with 8 transistor. So if we observe the output here, there is a improved version of the swing degradation of output, And with the by using this NGDI, which will reduce the transistor count, which in turn can reduce the silicon chip area, and modified GDI is an appropriate for design of low power high speed circuits, which will reduce the number of transistors on the. Now let us talk about the negative capacitance field effect transistor technology. Before, let me know about the negative capacitance field effect transistor technology. We all of them know about the subthreshold slope relation with MOS devices. What is subthreshold slope? Subthreshold slope is nothing but change in the gate voltage which is required to change in the drain current. So based on the subthreshold slope only, the FETs are divided into two categories. If the subthreshold slope is greater than 60 millivolts per decade, the devices under this category are MOSFET, FinFET, FDSP, etc. If the subthreshold slope is less than 60 millivolts per decade, the devices under this category are tunnel FET, NCFETs, etc. Let me now talk about the tunnel FET. A tunnel FET achieves a subthreshold slope that is less than 60 millivolts per decade, and it also achieves the low of current and low supply voltage. Due to the low on current, it results to band tunneling. And these are, let us discuss about the characteristics of the MOSFET and tunnel FET. Coming to tunnel MOSFET, it is indicate the MOSFET characteristic. A MOSFET is having the high off current as well as low on current. And coming to TFET, it is having the low off current and there is a little bit on current. Coming to the threshold voltage of MOSFET is high compared to the threshold voltage of TFET. Uh, the threshold voltage of TFET will achieve 60 millivolts per decade, and here it is a MOSFET structure and it is a TFET structure, band structure. So here the electrons move from source to drain. When the electrons acquire high potential, they are moving from valence band to the conduction band. In tunnel FET, due to this intrinsic region, the electrons will penetrate the barrier of valence band and to the conduction band. It will as it results to the band to band tunneling because the electrons have penetrate the barrier and enter into the drain. Now, due to the low on current in TFET, we move to the next technology, NCFET technology. Uh, NCFET is nothing but adding a thin layer of ferroelectric layer to the gate stack, which will enhance the surface potential and reduces the threshold voltage and maintain the low of current while amplifying the surface potential. A ferroelectric material is a material that can exhibit a spontaneous polarization, which can be reversed by the application of an external electric field. This device consumes less power without any loss of switching speed. It is a normal MOSFET structure and this is an NCFET structure. The major difference between the MOSFET and NCFET structures is in between the metal and gate oxide there is a ferroelectric layer. Due to by adding the ferroelectric layer to the gate stack which will resist to the negative capacitance. Coming to now here the full adder is implemented by using the GDA concept in NCFET technology. The full adder is implemented by using the gate diffusion input technique in NCFET technology with the help of 10 transistors, and this is the corresponding transient response of this full adder. Now, the full adder is implemented by using modified GDI concept in NCFET technology, and here the full adder is implemented by using the 8 transistors, and it is the corresponding out transient response of this full adder. What are the advantages by using this NCFET technology and with also help of the modified GDI technique? It improves the switching speed of the circuit as well as it will lower the power consumption. Let us talk about the improved switching speed of the circuit. Generally, NCFETs will enhance the switching speed of the full adder circuit. Negative capacitance effect counter-reacts the inherent capacitance of the FET, leading to a faster charging discharging of the internal nodes in the circuit. Coming to the lower power consumption, negative capacitance effects helps to boost the effective voltage gain of the transistor, which will enabling a low power supply voltage to be used without sacrificing the performance. Let us talk about the results and conclusion. Um, Here some of the results which we calculated by implementing the full adders with different techniques. Coming to the transistor count, in CMOS technology, we implemented full adder with GDA technique and modified GDA technique. And NCFET technology also we implemented full adder with GDA technique and modified GDA technique. Coming to this, we try to reduce the transistor count from 10 transistor to 8 transistor. Same in NCFET technology also. In GDA technique of full adder, we use the 10 transistor, and whereas for modified GDA technique, we reduce the transistor count to 8 transistor. Coming to the average power of GDA full adder in CMOS technology, 59.09 microvolts, and for modified GDA full adder in CMOS technology, 18.54 microvolts. If we observe if we observe the same full adders in NCFET technology we implemented, those of them having the average power of 6.768 microvolts, and the modified GDA, it is having 0.127. These are some of the delays calculated for these corresponding full adders, and is a power delay product. For GDA technique in CMOS technology, it is having the 297.2, and for modified GDA 75.3, and etc. These are the results we observed from this implementation. Firstly, with the help of GDA and modified GDA techniques, first we focus on the transistor count. So, by using this GDA and modified GDA technique, we reduce the transistor count that are required to implement full adder, thus reducing the power consumption as well as delay. Secondly, using the NCFET technology enhances the performance of the full adder by reducing the effective capacitance and increasing the effective transconductance of the transistors. And the proposed low power high speed full adder design having the several advantages over existing design. Um, Still, NCFET, there is ongoing research is happen in on NCFETs. It is worth nothing that NCFETs are still a relatively new technology, and further research and development are needed to fully explore their potential and address any challenges or limitation in the NCFET technology. And these are the some of the references corresponding work. Thank you for giving me this an opportunity.